Right. Let's unpack this. Today, we're diving deep into a really critical technical challenge in the world of building large language models, our LLMs.
hmm
It's all about getting these incredibly complex systems to truly understand and, maybe more importantly, align with what you, the user, actually want.
Right. It's not just about getting an answer, but the right kind of answer for a particular person or situation.
Exactly. You interact with an LLM, you give it a prompt, and you have an expectation. How does the model learn to meet that diverse range of expectations, not just, some generic good answer?
It's a fundamental problem, really, in making LLMs truly useful and, frankly, controllable. A key part of how we attempt this alignment currently is through reinforcement learning from human feedback, or RLHF.
Ah, yes, RLHF. We hear that acronym a lot.
We do. And within RLHF, a core technical component is reward modeling. This involves training a separate model whose job is essentially to predict what a human would prefer as a response to a given prompt.
Right. So the idea is if we can build a model that accurately scores potential responses based on what humans tend to like,
Mhm.
we can then use that score as a reward signal to train the main LLM itself, nudging it towards generating those higher scoring outputs.
Exactly. It's basically trying to mathematically represent human values, or at least preferences, for the model, like giving the LLM a compass pointing towards preferred by humans.
But here's where it gets really interesting, technically speaking, and where the standard approach kind of hits a wall. The common practice for this reward modeling relies heavily on something called the Bradley-Terry model.
Right, the BT model. It's very established.
And it's typically trained on data sets where humans have simply chosen between two responses, just saying, I prefer response A over response B, simple pairwise comparisons.
And the crucial, but as it turns out, flawed assumption built into using a single Bradley-Terry model trained this way is that there exists one universal truth, one single global reward function that captures everyone's preferences.
Ah, it assumes, in a sense, that if you just train hard enough on enough of those A vs B choices, you'll eventually converge on the definition of a good response that works for all humans, all contexts.
Which intuitively feels wrong, doesn't it?
It absolutely does. Human preferences are incredibly diverse. What one person finds helpful, another might find, I don't know, overly chatty or
Or
verbose.
one person wants creativity, another wants strict factual accuracy.
Exactly. Preferences are contextual, they're personal, they can even be contradictory depending on the situation or the person.
Precisely. And trying to squeeze all that richness and variation into a single mathematical function, a single reward model, well, that's a fundamental technical limitation.
So it means the model can't truly personalize its responses very well.
Right. It struggles to support a wide spectrum of valid but different user preferences. The paper we're looking at today calls this the challenge of achieving pluralistic alignment, getting the model to respect multiple viewpoints or styles.
And that brings us neatly to the source material for this deep dive. We have a fascinating technical paper here from researchers at the University of Illinois, Urbana-Champaign, Columbia University, and Rice University.
Hmm.
It's titled MiCRo, Mixture Modeling and Context-Aware Routing for Personalized Preference Learning. And this paper, it doesn't just highlight this problem of diverse preferences, it dives deep into the technical reasons why the standard approach falls short.
And importantly, it proposes a novel architectural and algorithmic solution to address it. It's not just pointing out the problem, it's offering a technical way forward.
It seems like a great example of research providing both, a solid theoretical backing for why we see this issue in practice and then a concrete technical path to potentially fix it.
Definitely. They really focus on the mechanisms required to learn and leverage these diverse preferences, specifically from the kind of data that's more readily available.
Perfect. So the mission for this deep dive is pretty clear then. We're going to understand the technical limitations inherent in current preference modeling techniques, explore exactly how this new framework, MiCRo, technically tackles the challenge of learning personalized preferences, especially without needing prohibitively expensive data, and delve into the implications of their approach and their experimental results for building, well, better aligned and more versatile LLMs.
And we're keeping our focus squarely on the technical mechanisms and the performance outcomes they demonstrate, right?
Exactly. Purely the technical angle today. So let's start by really digging into that core technical problem as the source material lays it out. You mentioned reward modeling learns a function to score responses. How is that formalized in the standard Bradley-Terry setup?
Right. So in the standard setup, you've got a prompt, let's call it X, and two potential responses, say, aw for the winner, the one a human preferred, and owl for the loser.
Okay.
The model learns a single reward function, let's call it R, that takes the prompt and a response, like X and awe, and outputs a score, a single number.
A score representing how good that response is for that prompt, according to this model.
Exactly. And the Bradley-Terry model then predicts the probability that a human would prefer awe over owl, given the prompt X, based only on the difference between the scores assigned by this single function R.
Ah, just the difference.
Just the difference. So the formula is P, Rx, Rx, R, Rx. Here is the logistic function, which just takes that score difference and natively squashes it into a probability between 0 and 1.
Okay, so the entire model is trained to make this single score difference predict the human's binary choice as accurately as possible, averaged across the whole dataset. The underlying assumption being that R represents the true preference function.
Precisely. And that's the problematic assumption, as we discussed. When you train this single model on a large, diverse data set of human preferences collected from many different people, maybe in different situations, you're implicitly assuming all those preferences were generated by the same underlying logic, that same single R.
But if the data set actually contains preferences from people who value, say, conciseness differently or safety versus helpfulness differently,
Yep.
then a single function simply cannot capture that complexity. It's like trying to average fundamentally different viewpoints into one single opinion. It doesn't really represent any of them accurately.
So you're trying to fit this multifaceted reality with essentially a single flat model.
Yeah.
What are the consequences of that, technically speaking? Does the model just perform poorly?
Well, it performs suboptimally, yes, but the paper provides a really compelling theoretical argument for why. They formalize this with what they call Assumption 3.1, the diversity assumption.
Okay.
It basically states, mathematically, that for any given prompt, there's a non-zero chance, a minimum probability, that any preference pair you observe could actually originate from one of several latent subpopulations. Let's say there are K different groups or types of users, and each group K has its own distinct preference function, Rk.
So it's formally positing that the data isn't monolithic. It's generated by a mixture of different preference types. Exactly. And building on that assumption, they have a key technical result, Theorem 3.2. This is where they mathematically show why a single Bradley-Terry model is fundamentally limited when faced with this kind of diverse data.
Okay, what does the theorem say?
It proves that when the true underlying preference distribution is indeed a mixture of these K distinct subpopulations, each following its own internal Bradley-Terry logic with its own reward function, then any single standard Bradley-Terry model attempting to fit this combined data inherently has an irreducible error.
An irreducible error, meaning no matter how much data you throw at it, no matter how perfectly you optimize that single model, it will never be able to fully capture the true preference distribution. There's a fundamental mismatch.
Exactly. There's a lower bound on how well it can fit the data, a minimum amount of error it's guaranteed to have, purely because of the underlying diversity it's trying to ignore or average out.
Wow, okay. And does the theorem give any insight into when this error is worse?
It does. The technical formula for this error lower bound, it's based on cross-entropy loss. It involves a couple of key terms. One relates to the variance of the score differences across the K subpopulations for a given prompt and pair of responses.
So if the different groups have wildly different opinions on which response is better.
Meaning they disagree more strongly, the variance is higher, and the unavoidable error for the single model gets larger.
Makes sense. What's the other term?
The other term relates to the entropy of the subpopulation distribution for that prompt. Colloquially, this means the more equally represented and distinct these diverse preference groups are in your data, if you have, say, 5 groups, and they all show up fairly often and have quite different tastes, the higher the entropy, and again, the larger the unavoidable error for a single model trying to capture them all.
So the more diverse your human feedback data truly is, in terms of both the strength of disagreement and the number of distinct groups, the worse a single reward model will fundamentally perform compared to what's theoretically possible if you could capture that diversity.
Precisely. It's a powerful theoretical anchor for the whole paper. It proves you must move beyond the single function assumption if you want to accurately model diverse human preferences found in real-world data.
Okay, that provides really solid motivation. And they touch on existing technical attempts to deal with this preference diversity, right? What are some of those, and why aren't they the perfect solution either?
Right, people have tried things. One obvious approach is to try and gather more fine-grained data. Instead of just asking which is better, A or B, You ask humans to rate responses on multiple specific dimensions like helpfulness, harmlessness, creativity, conciseness, and so on.
And then you could maybe train separate reward models for each dimension or a multi-objective model.
Exactly. That sounds intuitively like it should work better, and it can help. But the main technical hurdle there is data collection cost and scalability.
It's much harder to get those detailed ratings.
Significantly harder. Getting humans to provide consistent, reliable, multidimensional ratings is much more expensive and time-consuming than getting a simple pairwise preference. It's really difficult to scale this up to the massive data sets, millions of examples that are often used for training modern LLMs.
And you're also limited by the dimensions you predefine, I suppose. What if someone has a preference that doesn't fit neatly into helpfulness or creativity?
That's another good point. You might miss capturing preferences that fall outside your predefined categories. The paper mentions methods like ARMO, which is a strong multidimensional model, but it needed over 500,000 fine-grained labels to train. That just illustrates the sheer data requirement.
Okay, so fine-grained human data is often too expensive or difficult to get at scale. What about using AI models themselves to generate more detailed feedback? We hear about things like LLM as a judge.
That's another popular approach, yeah. You use a very large, capable LLM, maybe like GPT-4 or Claude, to evaluate responses from a smaller model and provide potentially more detailed feedback or even simulate different kinds of users.
But what are the drawbacks there?
Well, as the paper notes, this introduces potential fidelity issues. Is the judge LLM's evaluation really the same as a human's? It might not perfectly reflect true human preferences, and it might inherit or even amplify biases from its own training data. You're essentially getting potentially lower fidelity supervision compared to direct human feedback, even if it seems more detailed.
Okay, so the technical challenge remains crystal clear. We have lots of relatively cheap binary preference data, A versus B. We have limited, expensive, fine-grained, multidimensional data. How do we build a reward model that can capture diverse, personalized preferences effectively without requiring that dense, multidimensional supervision up front for the entire process?
And that is precisely the technical problem MiCRo is designed to solve. It proposes a two-stage framework, a clever technical pipeline, really, that aims to tackle this head-on.
2 stages. How does that work?
Think of it like this. Stage 1 focuses on uncovering the different types or dimensions of preference that are already hidden within that standard, large-scale binary preference data. And Stage 2 then learns how to efficiently apply the right type, or maybe a blend of types, based on the specific context or user instructions.
Okay. So instead of trying to force everyone's taste into one averaged model from the start.
Right. MiCRo tries to first learn several expert models in Stage 1. You could imagine each expert getting really good at capturing a specific style or dimension of preference, maybe one expert for concise and factual, another for creative and engaging.
And then Stage 2 is about choosing the right expert for the job.
Or maybe blending them. Stage 2 learns how to pick or combine these experts, depending on the situation, using additional context. Figure 1 in the paper gives a nice visual overview of this pipeline. Stage 1 trains a mixture of reward models. Stage 2 introduces a context-aware router that uses extra information to dynamically weight the influence of those different models learned in Stage 1.
So the final preference score isn't from just one model.
No, it's a weighted combination, a convex combination of the scores from the different models in the mixture with the weights determined by this router based on context.
This separation of concerns, learning the diverse experts first from broad data, then learning how to route to them based on specific context, that seems like a key technical design choice.
It really is. It's very strategic. It allows them to leverage those large, readily available binary data sets for the heavy lifting, the computationally intensive part of learning the core diverse components in Stage 1.
And then they can use potentially much smaller but contextually richer data sets for the more lightweight task of training just the router in Stage 2.
Exactly. It makes the personalization or adaptation part much more efficient.
Okay, let's zero in on Stage 1 then. Mixture modeling for diverse preferences. How do they technically learn these distinct reward functions from just that binary A over B data, which, as we said, doesn't explicitly tell you why A was preferred?
This is where their context-aware mixture modeling approach comes in. Instead of modeling the preference probability with a single Bradley-Terry model, like we discussed before.
P-U-L-L-R-L-X.
Right. Instead of that, they model it as a mixture of k different Bradley-Terry models. Imagine K parallel universes, each with its own preference logic.
Okay, K components in the mixture.
Each component K in this mixture corresponds to one of those latent preference types or subpopulations we talked about. And critically, each component has its own reward function. Let's call it RK.
Got it. So equation 1 in the paper formalizes this, right? It says the probability of observing a preference, over L for prompt X, is basically a weighted sum. For each component K, you multiply the probability that this preference even came from subpopulation K given the prompt
That's PA8CKX.
by the probability of the preference within that subpopulation K, which is just the standard BT probability using that component's reward function.
Exactly. You sum that product over all K components?
And crucially, you mentioned even in this first stage, there's some context awareness. The weight assigned to each component K, that PCKX term, it depends on the prompt X.
Yes, and this is a key technical detail. Even in stage 1, the model is learning to adjust the influence of the different preference components based on the input prompt itself. This is different from simpler mixture models, where those mixture weights might be static across all prompts, or maybe depend only on the responses themselves.
So even just from the prompt text, the model starts to learn, this prompt looks like it might need the factual expert, or this one sounds like it wants the creative expert.
Precisely. It's learning an initial prompt-based routing even during this first phase. In their implementation, each component's reward function is parameterized by its own set of weights. Let's call them GOOC, which are usually linear heads trained on top of a shared LL backbone model.
Okay, so they share the main LLM body but have different heads.
Yes, typically. And that mixture weight distribution over the K components, PZKX, is modeled by a separate small neural network, let's call it FES, that takes the prompt X as input and outputs K probabilities that sum to 1.
And how do they train this whole ensemble, the shared backbone, the K reward heads, and this prompt-based router network, FUF?
They train it all end-to-end by minimizing the negative log likelihood of the observed binary preferences over the entire large dataset, using that mixture model formulation from equation 1. This loss function is laid out in equation 2.
And what does minimizing that loss encourage the model to do?
Technically, it encourages the different reward heads, the ROOC functions, to differentiate themselves. They need to specialize in explaining different subsets or patterns within the preference data to collectively minimize the overall loss. So it naturally pushes them towards capturing different latent preference signals present in the binary data.
Okay, but you often hear about problems with training mixture models, right? Like, what stops all the heads from just learning the same average thing anyway? Or maybe one head just completely dominating and the others becoming useless. Mode collapse, I think it's called?
That's a very real risk and a crucial technical point they address directly. To prevent this mode collapse, where the model effectively ignores all but one or two heads, they add a regularization term during the stage 1 training. You can see it in equation 3.
What does this regularization term do?
It essentially encourages the output distribution of that prompt-based router network, FES to be more uniform across the K heads for any given prompt. It compares the router's output distribution to a uniform prior distribution using KL divergence.
So it's like a gentle nudge during training saying, hey, try to keep all the heads somewhat relevant. Don't just put all your probability mass on one favorite.
Exactly. It promotes diversity among the active heads. The final loss for stage 1, shown in equation 4, is just a weighted combination of the main negative log likelihood loss, equation 2, and this uniformity regularization term, equation 3. They used a weight of under 0.5 in their experiments.
And this combined objective helps ensure that the stage 1 training successfully disentangles those diverse preference signals into distinct, useful reward heads.
That's the goal, and the results suggest it works quite well.
Now, table 1 in the paper looked interesting. It compares MiCRo stage 1 to some prior approaches. What was the key technical distinction they highlighted?
They really emphasized MiCRo's use of context conditioning, even if just on the prompt X in this stage, within the reward objective itself. And they also pointed to the use of dynamic weighting via the hedge algorithm framework, which we'll get to more in stage 2, but the prompt-based router FEF is already a form of dynamic weighting.
And how does that compare to other methods?
It's distinct from, say, simpler static mixture approaches, where the weights between components don't change based on input, or from shared base ensemble methods like higher, where multiple heads are trained, but perhaps without this explicit mixture modeling objective and prompt-based weighting during the initial training. They call this dynamic context-aware aspect a crucial design difference.
Because it means the initial mixture training is already learning components that are inherently responsive to input characteristics, laying better groundwork for stage 2.
Exactly. It's setting the stage better for the more sophisticated context-aware routing that comes next.
Okay, so stage 1 gives us this toolbox, the set of K specialized reward heads, 1 through RK, each potentially capturing a different facet of human preference, all learned from standard binary data with this clever mixture modeling and regularization. But as you said, the stage 1 router FEF was only conditioned on the prompt X. How do we actually leverage additional context, things like explicit user instructions, maybe metadata, or specific criteria to pick the right head or blend of heads for a specific user or situation in the real world? That's stage 2, right?
That's exactly stage 2, context-aware routing for personalized preference learning. The key ideas here are sample efficiency and personalization, while stage 1 did the heavy lifting on massive binary data to learn the general diverse preference components.
Stage 2 focuses on adapting them.
Right. Stage 2 fine-tunes the router to use more specific contextual information, let's call it C. And C could be anything beyond the prompt explicit user preferences. I want a concise answer. Maybe demographic data, though the paper focuses on explicit criteria for its experiments, interaction history, or specific evaluation criteria provided alongside the data.
And the big technical advantage here you mentioned is that they don't need to retrain the potentially huge reward models, the rook heads or the backbone, from stage 1 when this new context C comes along.
Precisely. Retraining those large models every time you want to adapt to a new user type or context would be computationally infeasible. MiCRo Stage 2 ingeniously only fine-tunes the lightweight router network.
Ah, just the small route.
Just the router. And now this router takes both the prompt X and the additional context C as input, and it outputs the weights for the K Stage 1 heads. So FXXC gives you a probability distribution over the K components.
And this fine-tuning can happen with just a small amount of data.
Yes, that's the goal. It's designed to work with a small number of examples that are annotated with this concrete contextual information C. This makes it much more practical for real-world personalization or online adaptation.
How does the router actually learn which heads are best for a given context C? What's the mechanism?
They frame this using techniques from the field of online learning, specifically drawing on the hedge algorithm framework.
Hedge, like hedging your bets.
Sort of, yeah. You can think of the K reward heads learned in stage 1 as K different experts providing advice, in this case, preference scores. Now, suppose you get a new example that includes the prompt X, the context C, and the actual human preference, say, all was chosen overall.
Okay.
You can look back and see how well each of your K experts would have performed at predicting that specific outcome based on the scores they assign, or KX versus RKS. Some experts might have correctly predicted all, others might have gotten it wrong for that specific context. The hedge algorithm provides a principled way to adaptively update the weights you assign to these experts, which is what the router FUC does. Essentially, you give higher weight in the future to the experts, the reward heads, that performed better on the recent examples given the specific context.
So the router learns to associate certain contexts with certain expert success. If the context C is user wants a funny response, and one of the stage 1 heads, say head number 3, consistently gives higher scores to the responses humans actually found funny in the small training batch for this context.
Then the router FEF learns that when it sees context C funny, it should give a higher output weight to component K3.
Got it. It learns the mapping from context to expert weights based on performance on a small labeled set. How is this formalized in the training objective for the router?
They model the underlying user preference for a given example as a convex combination of the preferences predicted by the K latent heads. For example, I, with Prontic, context she, and W over ale, they calculate the loss for each head K on this example. Let's call it lease. This loss is basically how surprised head K was by the actual outcome formally. Lith equals dash log, PKII, WAILCI, where PK is the probability derived from head K scores.
Okay, so each head gets a loss score for each example.
Right. Then, the training objective for the router FRAKE is framed as an online mirror descent problem, regularized to keep the weights from changing too drastically. Equation 5 is the key update rule here. It calculates target weights, let's call them Bresh, for each head K on each example I.
Target weights, what are those?
These are like soft labels calculated based on the losses. Heads that had a lower loss mean they predicted the outcome better. For that specific example, I get assigned a higher target weight type. The calculation involves the losses and a temperature parameter, which controls how sharply the weights focus on the best performing heads.
Ah, so you use the performance of the fixed stage one heads on these few context-annotated examples to figure out what the router should have predicted as weights for that context.
Exactly. And then you train the actual router network FIC to produce those target weights, TOIC, when it's given the corresponding input. Ok, ik, key.
How is that training done?
That's outlined clearly in Algorithm 1. It's an iterative process. For each batch of context-annotated data, you first calculate the loss log for every stage 1 reward head K on each example I in the batch. Then you use equation 5 to compute those target weights TOIC. Finally, you perform a gradient descent step to update the parameters of the router network FEC, specifically by minimizing the cross-entropy loss between the router's output predictions, FEC, G, and these calculated target weights TOIC.
So it's supervised learning, but the supervision signal, the target weights, is derived dynamically from the performance of the stage 1 heads on the contextual data.
Precisely. It's a very clever way to leverage the diverse expertise learned in stage 1 for efficient adaptation in stage 2.
This whole two-stage approach seems to offer some pretty compelling technical advantages for actually deploying personalized models, doesn't it?
It really does. Two main ones stand out. First, as we've touched on, is efficiency. The really computationally expensive part, training the base reward heads and the shared backbone in stage 1, is done once, offline, on large, easily available binary data.
Right.
Stage 2 then only requires fine-tuning that small, lightweight router network F. This is much, much faster and requires far less data than retraining the entire reward model system. It makes personalization computationally feasible.
Okay, efficiency is key. What's the second advantage?
Generalizability. Because the router FEF is a learn-in function that explicitly takes context feature C as input to determine the weights, it has the potential to generalize to new contexts or unseen user types that it didn't explicitly see during its small fine-tuning phase.
How so?
Well, if new user provides context C that shares some features with contexts seen during training, the router might be able to make a reasonable prediction for the appropriate weights, even without having seen that exact context C before. This is different from some adaptation methods that might require labeled examples at inference time for every new situation to figure out the right weights. MiCRo's router learns the mapping itself.
So it learns the rule. If context looks like this, use experts these ways, rather than just memorizing weights for specific scene contexts.
That's the idea. It offers better generalization potential.
Okay, the theory and the architecture sound really promising. Let's talk about how they actually tested this framework. What was their experimental setup like?
To evaluate MiCRo, they used several different preference datasets. Two particularly important ones were HelpSteer2 and RPR.
Why those two?
Because they contain human evaluations across multiple distinct dimensions or attributes, things like helpfulness, correctness, coherence, safety, etc. This is crucial for testing stage 1, to see if MiCRo's individual heads actually learn to specialize in these different known dimensions of preference.
Makes sense. What other data did they use?
They also use Preference 700K, which is a much larger dataset consisting of standard binary pairwise preferences, more typical of what's used for large-scale RLHF training.
Now wait, if stage 1 training uses binary data, but HelpSteer2 and RPR have these multidimensional ratings, how did they convert those into the simple A over B format needed for stage 1?
That's a good question. They constructed binary pairs from the multidimensional ratings. For a given prompt and two responses in, say, RPR, they looked at each evaluation dimension separately. If response A had a higher absolute rating on helpfulness than response B, they created a binary training example labeled A preferred over B for the helpfulness aspect.
Ah, so they generated multiple binary pairs from a single multi-rated comparison, one pair for each dimension where the ratings differed.
Exactly. They did this for all dimensions and combined them into a large binary preference dataset. Importantly, they filtered out pairs where the ratings were identical on a dimension, and also pairs where all attributes were unanimously agreed upon for one response over the other.
Why filter out the unanimous ones?
To ensure the training data for stage 1 still contains some inherent signal diversity or disagreement. If every dimension always pointed the same way, it would be harder for the mixture model to learn to disentangle different aspects. They wanted to make sure there was some tension in the data for the model to resolve.
Smart. Creating a dataset where diversity is explicitly expected. What about the actual model they used for the reward functions?
They used GRM Llama 3.23b as the base model. That's a 3 billion parameter Llama model variant, which they kept frozen.
Frozen meaning its weights weren't updated during reward model training.
Correct. They only trained the components on top. Specifically for the K components in the mixture, they trained K separate linear probing heads on top of the frozen llama backbone. So the reward functions for ARC were just linear layers applied to the llama embeddings.
Keeping it relatively simple on the head architecture.
Yeah.
And the router network up there.
Also kept intentionally simple. For stage 2, it was just a single layer MLP, multi-layer perceptron, with 128 hidden units and a final softmax activation layer to output the K weights.
So they're really testing the framework itself, not relying on a super complex router.
Good. And who did they compare MiCRo against? What were the baselines?
They had a solid set of baselines to really isolate MiCRo's contributions.
Okay.
First, a single reward model. This is the standard approach. One Bradley-Terry model trained on all the binary data, your basic benchmark.
Second, a static mixture model. This was basically MiCRo's stage 1, without the context-aware routing during training, no prompt conditioning for weights, and without the hedge adaptation stage 2. It's similar to prior work like Maxman that learns a mixture, but with static component weights.
So isolating the effect of the dynamic weighting and routing.
Exactly. Third, a shared base ensemble model. This had an architecture similar to another prior method called higher, where multiple heads are trained on a shared backbone, but maybe without MiCRo's specific mixture modeling objective or regularization during training.
Got it. Any others?
Yes, two important ones representing different levels of supervision. They included fully supervised ARMO, which is an 8 billion parameter model, trained on over 500,000 fine-grained multidimensional labels. This is a very strong baseline showing what's possible with much richer, more expensive supervision.
Okay, the gold standard if you have the labels.
And finally, higher itself, which is that shared base ensemble baseline, but adapted using labeled examples available at test time, which is higher's proposed adaptation mechanism.
That's a comprehensive set. Covers standard methods, static mixtures, ensembles, stronger supervision, and test time adaptation. Okay, let's dive into the results. First up, the stage 1 evaluation. Did MiCRo technically succeed in disentangling diverse preferences just from that binary data they constructed?
This was a key test. They evaluated the individual heads that were learned in stage 1, before any stage 2 fine-tuning, to see how well each one aligned with the different known preference dimensions available in the Help Steer 2 and RPR test sets. Remember, those data sets have ground truth ratings for things like helpfulness, creativity, etc. 14 dimensions in total they looked at.
And Figure 2 in the paper shows this visually, right? With those radar charts.
Exactly. Figure 2 gives a great visual snapshot for a subset of dimensions. And the picture is quite compelling. The different MiCRo heads, trained only on binary data, did clearly learn to specialize, technically, in different evaluation dimensions.
So one head might score highly on helpfulness predictions, while another head learned from the same binary data scores highly on creativity predictions.
Precisely. And even more importantly, when they looked at the best performing head for MiCRo for each specific dimension, like which head was best at predicting helpfulness scores, that best head consistently outperformed the single reward model baseline, and also the other baselines trained purely on binary labels across virtually all 14 tested dimensions.
Wow. So the mixture modeling approach with the prompt conditioning and regularization actually worked to automatically carve up the diverse signals hidden in the simple binary data into specialized, meaningful components. Well, what about the quantitative improvements? How much better was it?
The numbers back up the visuals strongly. On average across the dimensions, MiCRo, using its best head per dimension, achieved a score of 0.921 on the RPR test set. That's a massive 40% relative improvement over the standard single-head baseline.
40%, that's huge.
It is. And it was also about 5.5% better than the static mixture baseline, showing the benefit of the prompt condition training. On the Help Steer 2 test set, it scored 0.81 on average, which was still a solid 6.8% improvement over the single-head and 1.1% over the static mixture.
And how did it compare to the shared base ensemble?
It also substantially outperformed the shared base ensemble baseline by over 20% relative on RPR and over 9% on Help Steer 2.
Okay, those are significant gains. It really validates the core idea of stage 1. You can learn diverse, specialized preference components effectively from standard binary data without needing explicit fine-grained labels for that initial heavy training phase.
Exactly. And Figure 3 adds a nice qualitative technical insight from stage 1 training. It shows heat maps of the initial weights assigned by the prompt-based router. F before stage 2 fine-tuning, for different kinds of input prompts.
What do those heat maps show?
They show that even just based on the prompt text, the router starts assigning varying weights to the different heads. For instance, a prompt asking for code might get higher weights assigned to heads that specialize in technical correctness, while a prompt asking for a story might activate heads specializing in creativity more. It suggests the model learned some degree of prompt-based specialization right in stage 1, which primes it well for the more complex context-aware routing later.
Very interesting. Okay, so stage 1 successfully learns the diverse experts. Now for the critical part, stage 2. Can MiCRo technically adapt these learned experts to personalized preferences using that additional context C? This is where the rubber meets the road for actual personalization, right?
Absolutely. This evaluation tested MiCRo's ability to use those explicit contextual signals. For the RPR dataset, the context C was the specific user criteria provided with the data, like focus on safety or be more engaging. For Help Steer 2, they augmented the prompts or used other metadata to simulate specific user needs or preferences as the context.
And they tested this in different scenarios.
Yes, two main scenarios. First, in-distribution evaluation. They fine-tuned the router using context-annotated examples from the training split of, say, Help Steer 2, and then tested its performance on the test split of Help Steer 2 using the same type of context. Same for RPR.
Training and testing on the same data distribution. What was the second scenario?
Cross-distribution generalization. This is a tougher test. They trained the router using context-annotated data from Help Steer 2 and the large Preference 700K dataset, but then tested its performance on the RPR dataset. This checks if the router can generalize what it learned about context to a potentially different user population or data source.
Okay, and you mentioned earlier the data budget for this stage 2 fine-tuning was small.
Extremely small, deliberately. For MiCRo, the router was fine-tuned using only 50 context-annotated examples per attribute or per context type drawn from the training data.
Just 50 examples. That's tiny compared to typical LLM training data sizes.
It really is. It's meant to simulate a realistic scenario where obtaining large amounts of preference data tied to specific user contexts is difficult or expensive. Can MiCRo adapt effectively with just a handful of examples?
So what did the in-distribution results show? Tables 2 and 3 in the paper.
Right. Correct. On Help Steer 2, Table 2, MiCRo, after fine-tuning its router with just those 50 examples per attribute, achieved an average test accuracy of 0.7830 in predicting which response would be preferred given the specific context.
And on RPR?
On RPR, Table 3, the average accuracy was even higher, 0.8218. And the crucial finding here is that MiCRo consistently outperformed all the baselines that were trained only with binary labels, the single reward, static mixture, shared base ensemble, across most individual attributes and certainly on average.
So that tiny amount of context-rich data used just to tune the lightweight router made a significant difference in adapting the model.
A huge difference. It's strong empirical evidence that the Stage 2 context-aware routing, using the hedge-inspired algorithm, is highly effective at adapting the diverse Stage 1 heads for personalized preferences, even with minimal supervision.
Now, how did it compare to the really strong baseline, the one using much richer supervision, that 8 billion parameter fully supervised ARMO model trained on 500,000 fine-grained labels?
This is perhaps one of the most striking results. MiCRo, despite using a smaller 3B parameter base model and relying only on that tiny Stage 2 fine-tuning budget of 50 contextual examples per attribute, rather than hundreds of thousands of fine-grained labels, performed competitively with ARMO on the RPR dataset.
Competitively, with that much less supervision.
Yes. And even more surprisingly, on the Help Steer 2 dataset, MiCRo actually outperformed the 8B ARMO model on average accuracy.
Wow. That really underscores the label efficiency of MiCRo's technical approach. It suggests you can achieve comparable or maybe even better performance on capturing personalized preferences with significantly less expensive and less demanding supervision just by being smart about how you use a little bit of context.
It's a very powerful demonstration, yes.
They also looked at that variation, MiCRo Hire, where they took MiCRo's Stage 1 heads and applied Hire's test time adaptation mechanism to them. What did that comparison reveal technically?
That was another key technical comparison. The result was that this MiCRo Hire variant, using MiCRo's heads but Hire's adaptation, significantly outperformed the original Hire baseline, which used its own ensemble heads.
What does that tell us?
It strongly indicates that MiCRo's Stage 1 training method, with a mixture modeling and prompt conditioning, produces a superior set of underlying disentangled reward heads compared to the heads trained by the standard ensemble method used in Hire. The foundation built in Stage 1 by MiCRo is simply stronger and better suited for adaptation, regardless of the specific adaptation method used later.
So the way MiCRo learns the initial experts is critical.
It seems so.
Hmm.
That initial training, even before the stage 2 router fine-tuning, creates a more robust technical foundation for capturing diverse preferences that can then be leveraged more effectively.
Okay. And what about the cross-distribution results in Table 4? Testing generalization to the RPR dataset after training the router on Help Steer 2 on the 700K data.
Those results further bolstered the case for MiCRo's generalizability. Even in this more challenging scenario, where the test data distribution might be quite different from the training distributions used for router fine-tuning, MiCRo using context again outperformed the other binary labeled baselines on average scores.
So the router showed some ability to apply what it learned about context to a new data set.
Yes, it demonstrates that the framework isn't just memorizing context weight mappings for one dataset, but learning relationships that can transfer to some extent, allowing it to adapt to user distributions or data sources it hasn't explicitly seen before, just based on the contextual information provided.
Taking all these results together, Stage 1 specialization, Stage 2 adaptation efficiency, strong performance compared to baselines, including fully supervised ones, and cross-distribution generalization, it really paints a clear picture, doesn't it?
It does. The experiments strongly suggest MiCRo is a practical, label-efficient technical solution for personalized preference learning in LLMs. It successfully learns diverse preference components from cheap data and then adapts them effectively using just a small amount of targeted contextual data.
And the ablation study they did, looking at the impact of that Stage 2 training budget, really drives home the efficiency point, right? Figure 4.
Absolutely. Figure 4 is very informative. It shows how the average accuracy of the context-aware router on the RPR and helps tier 2 test sets improves as you increase the number of context-labeled samples you give it during the stage 2 fine-tuning, going from 0 examples up to maybe 100 or 200 per attribute.
And what's the shape of those curves?
The curves show a very rapid improvement right at the beginning. Performance jumps significantly even with a very small budget. On RPR Figure 4a, the accuracy leaps from around 70.5% with 0 contextual examples, just using the prompt-based stage 1 router, to over 84% accuracy with just 50 examples per attribute.
Wow, a huge jump from just 50 examples.
Yes, and the gains continue after that, but they become much smaller. The law of diminishing returns kicks in quickly. A similar steep initial rise is seen on Help Steer 2, Figure 4b.
So this visually demonstrates that the router can technically adapt very effectively to personalized preferences using only a limited number of context-annotated samples. You get most of the benefit with just a handful of examples.
Exactly. You don't necessarily need thousands of specific examples for every single user type or context you want to support. A small targeted set might be enough to fine-tune the router effectively.
Which again is incredibly important for making personalized alignment practical in real-world deployment scenarios where collecting such data is often the bottleneck.
Definitely.
Now, of course, like any good research paper, they are upfront about the limitations of the current technical framework. What are some of the key hurdles or open areas they identify?
A major one they point out, which follows from our discussion of the experiments, is the technical reliance currently on having datasets that contain rich and consistent explicit user context C.
Right. Their stage 2 fine-tuning needs examples with that context label attached.
Exactly. Datasets like RPR, which have explicit user criteria annotated, are fantastic for demonstrating the method, but many standard large-scale preference datasets collected in the wild might not have this level of detailed, structured context consistently available for every preference pair.
So the current implementation works really well when you have those explicit context signals like make it concise or user demographic X. But the real world is often messier, and users might not always state their preferences so clearly.
Precisely. And this leads directly into what they highlight as a significant direction for future technical work: incorporating implicit user contexts into the routing process.
Implicit contexts, what does that mean technically?
It means moving beyond relying only on explicit instructions or predefined criteria provided alongside the data. It involves trying to learn or infer user preferences from more subtle signals that emerge naturally during interaction.
Like maybe patterns observed over a multi-turn dialogue. If a user keeps asking follow-up questions seeking clarification, maybe the router should learn to implicitly upweight heads related to clarity or detail for that user.
That's a perfect example. Or maybe behavioral signals. How quickly did the user accept a suggestion? Did they edit the response significantly? These could be implicit indicators of preference. The paper also mentions metadata like demographics, though they steered clear of using that in their experiments, focusing on task-specific criteria. But technically, any signal correlated with preference could potentially be used as context C.
But extracting and utilizing those kinds of subtle, implicit signals effectively for routing, that sounds like it adds another layer of technical complexity, doesn't it?
Oh, absolutely. It requires further technical development in areas like signal processing. How do you even capture that interaction pattern? Representation learning. How do you encode that pattern as input CE for the router? And robust user modeling within the LLM interaction flow. It's definitely a challenging but really important next step to make personalized alignment feel more seamless and natural without requiring users to constantly state their preferences explicitly.
Okay, so to bring this deep dive together and recap, we started by highlighting that fundamental technical limitation of standard reward modeling in RLHF, this attempt to fit the incredible diversity of human preferences into a single reward function.
Hmm.
And the paper we discussed formally proves this leads to an irreducible error, especially when preferences are truly diverse, as captured by their Theorem 3.2.
Right. The single model is fundamentally misspecified for the reality of pluralistic preferences.
And MiCRo offers this novel two-stage technical framework specifically designed to overcome this limitation. Stage 1 first learns a mixture of diverse reward functions, these specialized heads, directly from standard binary preference data, cleverly using prompt conditioning and regularization to disentangle different preference types without needing costly, fine-grained labels up front.
It finds the hidden structure in the cheap data.
Exactly. And then Stage 2 introduces a lightweight, context-aware router. This router is efficiently fine-tuned using just a small amount of data that does have contextual information, employing an online learning strategy like the hedge algorithm. This allows it to adaptively weight the pre-trained Stage 1 heads specifically for personalized preferences based on the given context C.
It learns how to use the experts effectively and efficiently.
And the experimental results really seem to technically validate this whole approach. The Stage 1 heads demonstrably specialize in different preference aspects. The Stage 2 router successfully adapted them using minimal context, achieving performance competitive with, or even exceeding, methods requiring far denser and more expensive supervision.
And it showed label efficiency and promising generalization capabilities, too.
Absolutely. It performs well, it's efficient, and it can even generalize to unseen user types or distributions to some extent, based on the context provided.
So this work really represents a meaningful technical step forward. It moves us closer to building LLMs that can genuinely move beyond generic helpfulness and start to truly understand and respond appropriately to individual needs, varied perspectives, and specific contexts, all driven by these technical advancements in how we model human preference.
It's a fascinating technical solution. So maybe a final thought for you, our listeners, to mull over, building on that discussion of limitations in future work. What technical methods could be developed to robustly extract and leverage those subtle implicit signals we just talked about? Think about signals from user interaction history, conversational dynamics, maybe even behavioral traces, not just explicit instructions. How do we turn that kind of implicit, often noisy behavioral data into a reliable technical signal C-up that the context-aware router in a system like MiCRo could actually use? Solving that seems like a huge, but potentially very rewarding challenge for making personalized AI truly seamless.